Okay, using the first approach, which is L min, we are going to use the L min equation. So since we have two duty cycle, so we will have two value of L min. So I put it as L min 1 and L min 2. So for L min 1, okay, we substitute the value inside the equation. So we will get 14.52 microhenry. For L min 2, okay, using duty cycle equals to 0.46, we will get the answer for L min 2 is 21.87 microhenry. Right, so among these two value, okay, we need to choose the higher value because we want to ensure that the converter is always operated in continuous conduction mode. So in order to do that, we need to choose the higher value of L. So we multiply by 1.25, so we will get L is 27.34 microhenry. Okay, that is using the first approach. Okay, and then using the second approach, okay, so using the second approach, what step? Okay, step number 4. Okay, second approach, which is delta IL is 40% of IL. So since we already calculated just now the value for inductor current, we have two value of inductor current, so obviously your delta IL will be 2 as well, right? So delta IL 1 to 0.4 multiplied by IL1, okay, we will get 0.9256 M. Okay, delta IL 2 0.4 multiplied by IL2, okay, you will get 0.75772 M. Okay, and then once we get this, the value for your delta IL, we can use this value in order to find the value for your inductor. Okay, so L1 will be equals to Vs dt over delta IL1. So substitute the value. Okay, over delta I1 will be equals to 0.9256. You will get 72.6 microhenry. Okay, L2 Vs dt over delta IL2. This is 2 as well, yeah? Okay, 18 0.46 okay over 0.7572, so you will get 109.35 microhenry. Okay, this is Vs2 Vs1. okay, right? So okay, for value for the using the second approach, value for inductor L1 and L2, if let's say that you compare from L min just now, okay, from the first approach, L min that we get is for L min 1 is 14.52 microhenry, while for L min 2 is 21.87 microhenry. So obviously the value for L1 and L2 using the second approach is much higher than the required element. So you can choose either one. Okay, you can choose 72.6 micro or 109.35 microhenry. Okay, mine it is better that you since these two value is already greater than L min, okay, it's better for us to choose the one that has a bit lower value, so that we will expect the losses is not going to be very big. Okay, so in this approach I'm going to choose L equals to L1, which is 72.6 microhenry. Okay, this value is already greater than the required L min. Okay, right, because we want to the losses will be not that big, so it will not affect so much on the efficiency. Less effect, I would say, less effect on the efficiency. Alright, okay, finally we're going to find the value for the capacitor. So find C. Okay, since inside the value for the capacitor we have the duty cycle, so we have 2 duty cycle, obviously the C will be 2 as well. Okay, you substitute the value, you will get C will be equals to C1 37.33 microfarad, and for C2, which is we are going to use duty cycle 2. Okay, in this example I'm using 1% of delta IL, the output voltage ripple. Okay, what is the answer will be 30.67 microfarad, 30.67 microfarad. Okay, for C2. Okay, so for capacitor, okay, like I mentioned previously, for the capacitor it doesn't matter so much which which value of capacitor that you're going to choose. So you can choose either one, either 37.33 or 30.67 should be okay. These two value is okay because it does not affect the boundary of the converter performance. Okay, so from the one that we write all the answer, we sum up into a table form. Okay, using the first approach in finding L and using the second approach in finding L. Okay, so from this example over here, if let's say that you only choose you only calculated using one approach, let's say using first approach, so you need to select your L will be equals to 27.34 microhenry and your C is 37 microfarad. So if let's say that you are using the second approach, okay, select the a bit lower L, okay, but make sure it is greater than L min. So L will be 72.6 microhenry and also C is 37 microfarad. So if let's say that you are doing both approaches, okay, first and second approach in the same question, okay, so you only select one value, so you need to select this value over here, okay, because it by selecting 72.6 microhenry it will cover because this is the higher value than 27.37, right? So this 72.6 microhenry will be covered for the first approach and also the second approach and finding the value of L. Okay, alright. Okay, now we proceed to example number 2. Okay, in this example over here, you need to design the converter to be operated in CCM. Okay, by using the value the variation of inductor current delta IL equation is 40% of average inductor current in finding the value of L, and then you need to find the maximum and minimum inductor current and also the source current, and finally you need to find the value for your capacitor. Okay, And then in this part B over here, if let's say that the output power is increased to 50 watt, okay, you need to determine whether the converter is still operated in the CCM or not. Okay, so and then you need to find the affected parameter and discuss your finding. Okay, in this question it just mentioned that the output power is increased to 50 watt. Okay, if we are referring to you need to refer to this table over here. So the output power is increased to 50 watt in part B. The rest is not being affected. Okay, the rest will maintain the same in part B. So the output voltage will maintain minus 12 volt. Okay, the source will maintain 24 volt. The switching frequency will be the same and the output voltage ripple will be the same in part B. Only the output power is changed from 25 watt to 50 watt. Okay. Okay, so let us try this exercise over here. Okay, first thing first, you need to find the duty cycle, obviously. Okay, the solution. First, find D, right? So D will be equals to, remember we need to omit the sign. Okay, 0.333. Okay, and then since R is not given, so we need to use the power that been given in order to help us in finding the value for R. Okay, so second, find R. Okay, R will be equals to V naught squared over P naught. So substitute the value 25, then you will get your R will be equals to 5.76 ohm. Okay, and then for the third one, find third step, you need to find your IL. Okay, IL will be equals to VST over R multiplied by 1 minus T to the power of 2. Okay. Right, 5. Okay, then you get your average inductor current will be equals to 3.1188 ampere. Okay. Alright, is it okay? Alright, and then we need to find our delta IL because we need to use this in order to find our L. Okay, your delta IL that you should get is 1.248 M. Alright, okay, and then your L Vs dt over delta IL. So substitute the value. Okay. F that been given is 100k over our delta IL. Okay, then we will get your inductor will be equals to 64.04 microhenry. Okay. Okay, and then in the question, this is step number 1, number 3. Yeah. Okay, in the question step number 4, in the question also asks you to find what is your IS, which is your input current or your source current. Okay, from the equation your IS will be equals to IL multiplied by D. Okay, so your IL is Okay, sorry for that. 3.1188 multiplied by 0.33 equals to 1.039 m. Okay, and then step number 5, we need to find our IL max and IL min. Okay, find IL max and IL min. Okay, IL max be equals to our average inductor current 3.1188 plus our delta IL is 1.248 over 2. You will get 3.7428 m. Okay, then for your IL min, okay, 3.1188 minus 1.248 over 2, you will get 2.495 m. Okay, finally, the last step, we need to find C. Alright, so your C is your duty cycle over your inductor, your resistor, sorry, 5.76 plus the output voltage ripple, which is 1%, and also your switching frequency 100k. Then you get your value for your capacitor is 57.81 microfarad. Okay, so that is the answer that you should get in order to solve for the part A. Okay, for part B is when the power being increased to 50 watt. Okay, for part B, P out equals to 50 watt, right? So first thing, since the output power is being increased, obviously it will affect the value for your resistor. Okay, you need to find the new resistor, the new value of resistor over 50. This will lead you, okay, 2.88 ohm. Okay, since your R is already changed, or what are the affected value, so you need to look at the equation, which equation that has R in it. Obviously it will be affected when we have a change. Alright, so delta IL, so the changes first will be your inductor current. Okay, here, which is 2.88, this is the R that will be affect the value for your inductor current. Okay, so you will get 6.238 m. Okay, so since delta IL equation is changed, obviously your delta IL will be changed as well. Okay, it's 2.495. Okay, your L will be affected as well. Okay, your L that you should get will be 32.03 microhenry. Okay, if you look back, refer back to in part A, you can see that the value of your inductor is being reduced by almost half, right? So so this is you need to check whether your converter is still operated in CCM or already fall into DCM. So how to do that? Okay, by using the L-min equation. If this L that we get 32.03 is greater than L-min, okay, so we know that our converter will still operate in CCM. If not, we know that it will fall into DCM. So you need to calculate the value of your L-min first, yeah. So L-min, so substitute the one that has the changes. Over 2. So L-min that you get is 6.41 microhenry. Okay, since L-min is that we get is less than the L in part B, so we know that the converter is still operated in CCM. Is in CCM. Okay, since our L is still greater than our L-min, the boundary, yeah. Okay, and then oops, I don't have okay, and then I just give the answer because I don't have space anymore. Okay, the IL max, which is the affected parameter, will be equals to 7.4855 m. Okay, IL min will be equals to 5 m, and also the value for your capacitor here, okay, 115.63 microfarad. Okay, so if let's say that in the question asks you to discuss, so you need to compare each one of these parameter, which one compare in part A and part B. Okay, so whenever the output power is increased, your R load will be decreased, right? You can see that the one in part B is smaller R as compared to in part A. Okay, and then but your inductor current will be increased because the use of smaller R in the denominator. Okay, your L, okay, the value of inductor will be decreased once we increase the value of output power. Okay, and then the value of your capacitor will be increased. Okay, so these are the changes, the affected parameter once we change the output power. Is it either increase or decrease? So you need to check, okay, and then compare, right? And then for this part 3, example number 3 over here. Okay, example number 3 over here is quite simple. Okay, this graph over here, maybe some of you already seen this graph over here because this is come up in your one of your test set. Okay, almost similar waveform. Okay, so you are required to design a buck boost converter. Okay, and so it gives you the output voltage ripple in this figure 1 over here, and the load resistor is 20 ohm. So you need to find the VS, source voltage, switching frequency, duty cycle, the value of inductor, the IL, average inductor current, and the value for the capacitor. Okay, so in this example over here, since duty cycle is not given and also the input voltage also is not given, okay, it gives you only the output voltage. Okay, where we can find the output voltage is this one over here. Okay, this is the average output voltage, yeah. Okay, this is this point over here, okay, is your V0 max, and this point over here is your V0 min. Okay, right, we have your T on here, will be equals to 12 microsecond, and your T here will be equals to 20 microsecond. So these two information will help you in finding the value of your duty cycle. Okay, so first find D. Okay, we need to use this equation, T on over T. T on in this example is 12 micro. Switching time is 20 micro, so you will get 0.6. Alright, and then next step, you need to find your switching frequency, right? So switching frequency, since the switching time is given, so switching frequency will be equals to 1 over T. Okay, which is it will be equals to 50 kilohertz. Okay, and then step number 3, we need to find our Vs, right? Okay, use the duty cycle equation that relate between the output and input voltage. Okay, D will be equals to V0 over Vs plus V0. Okay, you substitute all the known value. Okay, so we have 0.3 over here will be equals to 15 over Vs is the one that we want to find, plus V0 here will be equals to 15. Sorry, 15 here. Okay, so you rearrange what we call rearrange the equation in order to take out your Vs. Okay, so you will get this. Alright, and then your Vs that you will get is 10 volt. Okay, right, and then for step number 4, find L-min. In this example, it doesn't mention whether which approach that you're going to use. So you can use the first approach or the second approach. Okay, in this example, I'm using the first approach, which is finding the L-min first, and then we multiply by 1.25. Okay, so L-min will be equals to 20 multiplied by our switching time. Okay, multiplied by 1 our duty cycle over 2. So we will get 32 microhenry, and then our L 1.25 multiplied by 32 micro, we will get 40 microhenry. Okay, and then what else? Okay, finally the last one, okay, so the last one over here, find C. Okay, in order to find C, since the output voltage ripple is not given, but the information from the figure 1 is there, so V0, delta V0 over V0 will be equals to this. Delta V0 is actually V0 max minus V0 min over V0. Okay, which is 15.15 minus 14.85 over our average, which is 15. You will get output voltage ripple is 0.02. Okay, and then once you get once you get this one over here, you can substitute in finding your C. So the value of the capacitor you should get is 30 microfarad. Okay, so that's it, the solution for example number 3. Okay, so finally this is I'm coming to the end of the lecture. Right, so we go for the a bit of knowledge on the limitation of single stage conversion. Single stage, which means that you have only what we call only a resistor, okay, which is one resistor, okay, one inductor and one capacitor in your circuit. So buck boost and buck boost, they are considered a single stage conversion. Okay, so okay, what is the limitation of single stage conversion? So actually, what is the limitation of buck boost and buck boost converter? Okay, you can see here the output power of this regulator is small because due to the limitation of the current handling of a single transistor or a single switch. Okay, and then at the higher current, the size of this component increases. Okay, so at higher current, so we need to increase the value of L, we need to increase the value of capacitor in order to cope with the higher current. So with higher value of capacitor, it will lead you to higher component losses and it will affect your efficiency. Okay, and then since this is a non-isolated DC to DC converter, obviously there is no isolation between your input and output voltage, and this is not really a good what we call option if let's say that you are doing an application in high power application or in high current application. We need to have this isolation in this converter. Okay, so for high power application, okay, normally we will use multi conversion, whereby multi conversion, which is we have more than one switches, active switches in the circuit, so that it will be in terms of current handling will be better, in terms of the what we call the isolation also will be protected. Okay. Right, so in this table over here, I sum up the important what we call equation among these three converter in buck boost and buck boost. Okay, you can have a look at this. Okay, what we call in finding the value of the capacitor here for buck and for boost and buck boost, they are using the same equation. Do remember that. So if let's say that in the final it doesn't give you the equation, I mean like the equation for the capacitor for buck boost, you can refer to the boost because they are using the same equation. Okay, right, so finally the last slide. Okay, so DC to DC converter are capable in transferring energy only in one direction, because this is DC, you cannot use bidirection. Okay, bidirection must be an AC. Yeah. Okay, so a switch mode, okay, this is comparing to the linear regulator, which is it. Remember, in linear regulator it does not have the freewheeling diode and also the capacitor. All right, so we compare to a switch mode. Switch mode converter, it has the freewheeling and the capacitor. Okay, in order to handle with the what we call in the current and also in the ripple. Okay, so a switch mode DC to DC converter is much more efficient in as compared to linear regulator because of reduced losses in the electronic switches, because we have the diode, so it does not burden the switch so much. So when the switch is off, the diode will take place, right? Okay, DCM for DC to DC converter is possible and sometimes desirable. It's depend on the application. Okay, however, the input output relationship is a bit different than the one that we did in CCM. Yeah. Okay, okay, and then so a buck converter has an output less than the input. Boost, the output is higher than the input, and buck boost, it has both. It can be either higher and lower. So I hope all of you able to follow through the slide and try to do all the example, so we can, if you have any problem, we can discuss. You can write the comment in Google Classroom or in the YouTube channel. Okay, I will try my best to answer all of the question. Okay, so till then, so take care. I end the lecture, this lecture today. Okay, so stay at home. Okay, I see you soon, hopefully face to face, once the MCO being lifted. Okay, bye. Assalamualaikum.